Welcome to our exploration of astrodynamics, the fascinating study of the motion of celestial bodies in spacecraft. In this video, we will delve into the principles and applications of this compelling field within aerospace engineering. Astrodynamics is integral to our understanding of how objects like planets, moons, and satellites move through space. But why is it so important? By mastering these dynamics, we unlock the secrets of space travel that ensuring safe and efficient paths for satellites and spacecraft. We will journey from the earliest theories of celestial motion to today's cutting-edge advancements. We'll trace the historical development of astrodynamics, explore key innovations, and address the challenges and breakthroughs that have shaped this field. Whether you're a student, an aerospace enthusiast, or a professional in the industry, this video is designed to enrich your understanding and appreciation of astrodynamics. So let's embark on this journey together and discover the wonders of how we navigate the vast expanse of space. As we move forward, you'll see how ancient astronomers laid the groundwork for modern astrodynamics. Get ready to be inspired. Our journey into astrodynamics begins with the early theories of celestial motion, tracing back to ancient Greek astronomy. The Ptolemaic system, with its intricate epicycles and deferents, dominated our understanding of the heavens for centuries. Yet, it was the revolutionary ideas of Copernicus, who placed the sun at the center of the universe, that ignited the shift from geocentric to heliocentric models. This marked the dawn of a new era in celestial mechanics. Through these early milestones, we lay the foundation for our exploration of the cosmos. As we delve into the contributions of Kepler, Newton, and beyond, you'll see how these ancient insights evolved into the precise science guiding modern spacecraft. Now, let's continue our adventure by examining Kepler's groundbreaking laws of planetary motion. Building on revolutionary ideas, Johannes Kepler's contributions brought new understanding to planetary motion. Kepler's first law, known as the law of ellipses, states that planets move in elliptical orbits with the sun at one focus, a departure from the earlier theory of circular orbits. Kepler's second law, or the law of equal areas, describes how a line connecting a planet to the sun sweeps out equal areas in equal times, meaning planets move faster when closer to the sun and slower when further away. Lastly, Kepler's third law, the law of harmonies, reveals a precise relationship between the time a planet takes to orbit the sun and its average distance from the sun. These three laws provided a needed mathematical framework for celestial mechanics, revolutionizing astrodynamics and paving the way for future discoveries. As we move forward, you'll see how these foundational principles led to Newton's law of universal gravitation. Isaac Newton's groundbreaking law of universal gravitation laid the cornerstone for modern astrodynamics, forever altering our understanding of celestial mechanics. This principle explains how every particle of matter in the universe attracts every other particle with a force directly proportional to their masses and inversely proportional to the square of the distance between them. Newton's insight into gravitational forces unified the heavens and Earth, allowing for precise calculation of spacecraft trajectories and orbital paths. By quantifying the gravitational pull, we can predict the motion of planets, satellites, and space probes with remarkable accuracy. This profound understanding has had an indelible impact on astrodynamics, driving advancements in space exploration and navigation. As we delve deeper into the intricacies of gravitational influence, we'll uncover how Newton's law continues to shape our quest for the stars. Stay with us as we explore more revolutionary milestones defining astrodynamics. The space age marked a monumental leap in astrodynamics, transforming the way we understand and navigate space. Starting with the historic launch of Sputnik in 1957, humanity entered a new era where space was no longer the realm of dreams, but of reality. The world watched in awe as the Apollo missions took us to the moon, representing a pinnacle of human achievement and engineering prowess. These missions provided invaluable data that refined our knowledge of spacecraft motion and navigation. Advancements in spacecraft navigation became pivotal, with innovations like precise orbital calculations and real-time trajectory adjustments, allowing unprecedented control and efficiency in space travel. This era revolutionized our capabilities, laying the groundwork for today's sophisticated space missions. As we move forward, you'll see how these advancements set the stage for even more intricate and ambitious endeavors in modern astrodynamics, showcasing the incredible progress we've made and the limitless possibilities ahead. Let's delve into the fascinating realm of orbital mechanics and spacecraft trajectories. Orbital mechanics deciphers the paths spacecraft follow, from circular to elliptical orbits, each serving distinct purposes and missions. Navigating these orbits, spacecraft undergo orbital maneuvers, a series of precise adjustments that alter their trajectory for tasks like docking, satellite deployment, or interplanetary travel. Trajectory planning, the art of charting a spacecraft's course, is where science meets strategy. Engineers meticulously map out these journeys, accounting for gravitational influences to achieve mission success. The principles of orbital mechanics are not just theoretical, but practical, guiding real-world missions and groundbreaking accomplishments in space exploration. As we move forward, you'll see how these principles are applied in overcoming the challenges of astrodynamics, bringing us closer to our exploration goals. Astrodynamics presents many challenges that test the limits of our engineering ingenuity. Gravitational perturbations, for instance, can dramatically affect the orbits of satellites and spacecraft, necessitating constant adjustments. Moreover, space debris poses significant risks to missions, with even tiny fragments capable of causing massive damage upon collision. For interplanetary travel, the complexities multiply, requiring advanced computational methods and meticulous planning. But these challenges also drive innovation, pushing the boundaries of what we can achieve in space. As we delve deeper into the science of astrodynamics, new solutions and technologies emerge, paving the way for safer and more efficient space exploration. As we move forward, you'll see how breakthroughs in computational astrodynamics have revolutionized the field, making what once seemed impossible, possible. Stay tuned as we explore these exciting developments. The field of astrodynamics has undergone a remarkable transformation thanks to recent advances in computational methods. Pioneering numerical techniques have allowed scientists to solve complex equations with unprecedented accuracy, opening new avenues for research and application. Simulation software, a vital tool in modern astrodynamics, now offers detailed and realistic models that predict the movement of celestial bodies and spacecraft with remarkable precision. Moreover, optimization techniques have streamlined mission planning, enabling more efficient and cost-effective space missions. These breakthroughs are not just academic triumphs, they are the backbone of our current and future space exploration endeavors. As we continue this journey, you'll discover how these computational innovations are preparing us for the next frontier. Stay tuned as we unveil more about their groundbreaking impact. Astrodynamics has a wide array of modern applications crucial to the advancement of aerospace engineering. One of the primary applications is satellite deployment. Through precise calculations and understanding of orbital mechanics, we can place satellites into specific orbits, enabling communication, weather monitoring, and global positioning systems. Another significant application is in space exploration. Astrodynamics aids in planning and executing missions to distant planets, gathering invaluable scientific data. Moreover, the principles of astrodynamics are integral to defense systems, from missile guidance to satellite surveillance, ensuring national security and strategic advantages. As we've seen, astrodynamics is more than just theoretical. Its practical applications are vast and impactful. As we move forward, you'll see the exciting future prospects of astrodynamics in our next segment. As we conclude our exploration, let's look ahead to the exciting future of astrodynamics. Emerging technologies are pushing the boundaries of what's possible, promising faster and more efficient space missions. Space tourism, once a dream, is now on the horizon, poised to open the cosmos to everyone. With advancements in propulsion and navigation, interstellar travel is no longer confined to science fiction. These developments are not just incremental steps, but revolutionary leaps that will transform how humanity interacts with the universe. The future of astrodynamics is indeed a bright tapestry of innovation and curiosity. Stay tuned as we explore more groundbreaking topics and continue our journey through the stars. Thank you for joining us on this fascinating journey through astrodynamics. We've explored the evolution of celestial mechanics from ancient theories to modern-day advancements and celebrated the incredible milestones that have shaped our understanding of space. But this is just the beginning. Astrodynamics plays a crucial role in our quest to conquer the cosmos, and there's always more to learn. If you found this exploration inspiring, there's a world of information waiting for you. Don't miss out on our future content. Subscribe to our channel and follow us for the latest updates and exciting new videos. Dive deeper into the science that propels us beyond our planet and join a community of learners and enthusiasts dedicated to exploring the final frontier. The cosmos is vast and full of mysteries. Let's continue.
The Cassini mission has been exploring the Saturn system for nearly 13 years and has rewritten the textbooks on the ringed planet and its moons. But the spacecraft is pretty much out of fuel. Following NASA's planetary protection guidelines, the mission will end with Cassini plunging into Saturn's atmosphere. But before that happens, scientists and engineers have planned an exciting grand finale that promises some of the most amazing science and images of the whole mission. So how are they going to pull this off? Well, it really is going to take a special kind of crazy engineering. I am here with Morgan. She's a scientist on the Cassini project. The grand finale, it's going to be 22 orbits, about 6 months. What do we hope to accomplish in that amount of time?
We hope to accomplish a lot of incredible science, things that we have never been able to do before with the Cassini mission. We're going to go screaming over the top of Saturn. We'll be able to study the hexagon of Saturn's North Pole in greater detail than ever before. We're going to go shooting between Saturn and its rings, threading the needle, which means we'll be able to taste the ring particles, be able to understand more about what those are made of. We'll also be able to taste the atmosphere of Saturn. We're also going to get a better idea of the interior structure, since we'll be getting closer to Saturn than we've ever been. And then this will all culminate in Cassini's final plunge into Saturn's atmosphere, taking data for as long as possible and transmitting that back to Earth. To be able to do this engineering, to thread that needle between Saturn and its rings, is really challenging. That requires something called astrodynamics.
Okay, so what is astrodynamics? It's a form of engineering, but when we think about engineering typically, we think about people who are using physics and technology to build stuff. Astrodynamicists are building flight paths that will take our spacecraft to where they need to go. Let's go talk to one of the engineers who's pivotal in the design of this flight path on the Cassini spacecraft. Okay, this is Brent. He's our astrodynamicist at JPL. Brent, what makes the grand finale particularly difficult and challenging?
The grand finale is a series of 22 orbits where the periapsis, or the closest point of the orbit, is actually in this gap between the upper atmosphere of Saturn and the innermost part of the main rings. What we've done is we've designed this trajectory such that, utilizing one last Titan gravity assist, we can jump the entire ring system and place the spacecraft orbit inside this very, very small gap that's only 2,000 kilometers wide.
This concept of gravity assist, I think a lot of people have heard of it, but maybe not completely understand it.
What it essentially means is you're harnessing the gravity of a body that's orbiting another body. For Cassini, Titan, a very massive moon, is orbiting Saturn. If Cassini is also orbiting Saturn, I can fly very close to Titan. Depending on if I fly in front of, or behind, or above, or below, I can use that gravity to bend my trajectory. We harness that power. It's our engine, it's our tour design engine. As soon as we do that last Titan flyby, Cassini's fate is sealed. It is going to impact Saturn no matter what.
So, some really amazing science before we take this final plunge into Saturn. And let's remember why we're doing that. Why are we flying the spacecraft into the planet? It's to protect the moons of Saturn. For example, Enceladus, this great moon that has an ocean underneath the surface, it might just be this cozy little place for microbes to live. Now, if you look at our spacecraft, we try to keep it as clean as possible, but there's a real chance that we're bringing microbes from Earth with us. There's no way to avoid it. We want the moon as pristine as possible for future missions to go exploring.
Orbital mechanics can defy our normal expectations of motion. And in this animation, we'll see how. But to understand how, let's first review a few things. Why we need to go into an orbit to stay in space, what mechanical energy is, and we'll also learn all about orbital maneuvers. We will then look at why, when navigating in an orbit, we need to slow down our spacecraft to move faster and speed up to go slower. First of all, what makes up an orbit? Is it just how far we are from Earth's surface? Well, if we place the SpaceX Crew Dragon capsule hundreds of kilometers above Earth with no velocity, gravity, represented by the blue arrow, will pull on it, and it will follow the trajectory of this blue line and fall out of the sky towards Earth. But if we give it some horizontal velocity, represented by the red arrow, the trajectory begins to change. And if you move fast enough horizontally, the spacecraft will never hit Earth. These high velocities that are required to achieve orbit can only be accomplished with the absence of air resistance. So therefore, the rocket has to have a high enough altitude to be out of the dense atmosphere. This speed and altitude of the spacecraft gives the spacecraft kinetic and potential energy. Kinetic energy from how fast it's going, and potential energy from how high it is, or its altitude. These two forms of energy, added together, make up mechanical energy and can be calculated through this formula. A great illustration of mechanical energy is a roller coaster. A roller coaster train will have constant mechanical energy but will continually exchange kinetic energy for potential energy and vice versa depending on where it is on the track. As it rises away from Earth, it slows down, lowering its kinetic energy but increasing its gravitational potential energy. And as it falls to Earth, the opposite is true. A perfectly circular orbit will have a constant kinetic and potential energy throughout each orbital period if the orbiting altitude is constant. But orbits are never perfectly circular, meaning they are elliptic. An elliptical orbit will have a point that is closest to its orbiting body, which is referred to as the periapsis, and a point where the orbital height is the furthest from its orbiting body, which is referred to as the apoapsis. When talking about a spacecraft orbiting Earth, these 2 points are referred to as the perigee and apogee. Manipulating the size, shape, and angle of your orbit makes up a large portion of understanding orbital mechanics. Let's briefly review different ways of manipulating orbits to ultimately understand why we need to slow down our spacecraft to go faster and speed up to go slower. The most common burns that are used are the prograde and retrograde burns. Prograde and retrograde burns are burns whose burn vectors are parallel with the direction of motion. Let's look at a specific example of each. First, the prograde burn. The prograde burn is when you fire your engines into the direction you came from. A prograde burn will increase your velocity or kinetic energy at that specific point, but not your altitude or potential energy. But as you continue in your orbit with higher kinetic energy, your inertia will cause your outward centrifugal force to be higher than that of gravity, resulting in you to slowly fall further and further from Earth as you climb in altitude. Your orbit will now be elliptic and look like this. Now let's look at that again. Your added inertia and centrifugal force is now a little stronger than before, and this causes you to resist gravity a little more, resulting in you to fall away from Earth. If we were to fire our engines in the exact opposite direction, this would be a retrograde burn, and it is very similar to a prograde burn, but in the exact opposite direction. It therefore subtracts kinetic energy from the orbit at that point of where you fired your engines, and this will affect the altitude of the opposite side of your orbit, bringing it closer to Earth. Now, if you want to increase your orbit's altitude, can't you just fire your engines at Earth instead of a prograde burn? Well, let's do it and see what happens. This burn is known as a radial out burn. A radial out burn will result in your spacecraft to resist the effects of gravity to an extent, maintaining a more straight trajectory throughout the burn. But because there's no velocity added to your orbit, as you raise your altitude from Earth, you slow down. This will pull the opposite side of your orbit towards Earth. The result is that your orbit rotates about your spacecraft with no substantial energy gain. A radial in-burn, where you fire your rockets towards space, will have the same effect but in reverse, like this. The last types of burns that can be made are the normal and anti-normal burns. The normal and anti-normal burns are perpendicular to your direction of motion. As you complete a normal burn, your rocket begins to rise up away from your initial orbit. But because you are still orbiting a planet, your orbit will slowly rotate, with the center of rotation being the planet you orbit. This change in orbit is referred to as an inclination change and is a rather fuel-costly maneuver. They are generally only used for corrections when matching the orbit of another spacecraft. Now that we've reviewed the basics of orbital mechanics, let's use what we learned to try to navigate in an orbit. Let's look at a real-life example. A SpaceX Dragon capsule rendezvousing with the ISS. Say you are in the same orbital path as the ISS, with it just in front of you. Intuitively, we'll fire our rockets behind us to go closer to it, a prograde burn. Let's see how this affects your orbit relative to the ISS. This increased kinetic energy will begin to increase the outward centrifugal force, pulling the spacecraft away from Earth faster than Earth's gravity can pull back on it. This in return causes the rocket to gain altitude or potential energy, and therefore lose kinetic energy, much like a roller coaster on the incline part of a track. This gain in potential energy results in the spacecraft to lose kinetic energy. Our new orbit now has a higher altitude and therefore a slower average speed. The Moon's orbit is a great example of this higher and slower orbit, as it takes a month to orbit the Earth. If we follow the position of our spacecraft relative to the ISS, it will rise up above the ISS and fall further behind as a result of this longer orbital period. Well, what if we do just the opposite? Let's try firing our rockets into the direction we are heading, a retrograde burn, slowing us down to see what happens. If we fire our rockets in this direction, we'll decrease our kinetic energy at that point, and our potential energy remains the same. But as we continue to orbit, the decrease in kinetic energy will result in the spacecraft being pulled to Earth faster than our inertia pulls it away. This will cause an exchange of energy from potential to kinetic energy. Now, if we follow the path of the orbit relative to the ISS, we will begin to approach it as we pass under it. This only leaves us with one problem. We are only at the correct orbit as the ISS at one point, our apoapsis. A last prograde burn is required to now circularize the orbit to replicate the orbit of the ISS.